Okay, this is example number 3 on the back of the pink notes that we got today. Pink sheet on the back, doing number 3. The number got erased, the very first one. And the goal is what is the force that I need to put at the 40 centimeter mark on the meter stick in order to make this remain balanced. I'm going to call this FA, and I've got it in green. And the lever arm for A is from where it is all the way to the center point, the fulcrum. So if this is a 0 mark on the meter stick and this is a 50 mark in between the two, the lever arm is 50 centimeters. For this one, I'm going to call it FB. That's what I don't know. The lever arm for FB is 10 centimeters because it's from the 40 mark to the 50 mark. So it's 10 centimeters between here and here. I don't care that it's at the 40. What's important is the distance from where this is being hung to the center fulcrum point. And then the last one, this is FC. And again, if it's hung at the 100 centimeter mark and the 50 centimeter mark is the fulcrum, then this makes this lever arm 50 as well. Using my equilibrium equation to balance everything, it's the sum of the forces, it's the sum of the torques making it want to go counterclockwise have to add up and equal the sum of all the torques making it go clockwise. Now I just need to figure out which one of these is clockwise and which one's making it go counterclockwise. So starting with the green one, the A force, if I hold my pen where the pivot point is and I push down just like the arrow for A is, it makes it pivot in a counterclockwise manner. So I'm going to put that over here on this side. I'm just going to write down the ones that I have causing counterclockwise. So the torque from A is on the counterclockwise side. All right, B, again, if I hold here at the pivot point and I push down right where B is, ignoring the A and the C, just B alone, makes this want to turn backwards, counterclockwise. So that'll go over here on this side as well. And then the last one, C, if I hold it in the center and I push down here, then it makes it want to rotate clockwise, so it goes on the other side. Instead of just saying the torque caused by A, I can actually plug in the equation for it. This is FA LA. That's just what this is. And just do that for all the terms. FB LB, C LC. And as long as you've got what is on the counterclockwise side and the clockwise side separated out correctly, and you have your lever arms labeled correctly, from here out it gets really easy. You just plug in and solve. So I have 25 and 50 centimeters. Here I have my unknown and 10 centimeters. And over here I have 30 and 50 centimeters. So all I did was just plug in. That's FC LC. And then solve. Now, since these are all in centimeters and this is an equilibrium problem, I don't have to convert. Because if I did, there would be a conversion factor in every single one of these terms and it would cancel. So if it's an equilibrium problem, that's really nice and we kind of get to take some shortcuts. As long as all of the forces are in newtons and as long as all of the lever arms are measured in centimeters, I don't have to convert. Finish solving. And the force at B, in order to keep this in equilibrium, needs to be 25 newtons.